This is my CNC converted Harrison milling machine, which I've used in quite a few videos. I'm going to describe an attachment I'm making for it in this video. The machine has a horizontal spindle and a vertical spindle here, which is hanging from the ceiling because it's heavy and it's easy to handle on the chain blocks. It's a nice machine, I like it quite a lot, but the spindle speeds are really rather slow by modern standards. If you look around the back, there's the speeds plate here, and you can see it's got a minimum of 45 RPM and a maximum of 1000 RPM, which is very slow. So here's the plan. I'm going to make an adapter which takes a 24,000 RPM spindle from eBay. These are really quite inexpensive. It's going to be free to rotate to any angle, though going this far is probably pointless. You can never tell. It will clip onto the existing dovetail overarm which supports the outrigger bearing when in horizontal mode, and it clips onto that dovetail using the same bolts or same style of bolts as hold the dovetail to the machine itself, and then it is held on to the dovetail adapter by a circular T-slot in the style of those used to hold down compound slides on lathes. Because this is a machine tool application and because it's traditional, I'm using cast iron for the parts of this adapter. Machining the adapter plate was a fairly simple piece of lathe work, so I won't spend too much time on that. What is slightly more interesting than the machining for this part is the pattern, which was 3D printed. It's a loose piece pattern, which is something you don't see mentioned very much, but I've seen Myford Boy do one on YouTube as well. This particular one was 3D printed. It's set in the sand, as it is here, then inverted. Then what you do is you take out the front part, the main part, like this. Then you can slide in the small segments into the revealed space by removing the main part, and that leaves behind cavities in the sand which form the undercuts. The piece of MDF on the back of the pattern was added by the foundry man because I forgot that he needs something he can put screws in. Because the part requires an uninterrupted front face so that the T-nuts don't pop out, I've had to make an access hole at the back, and also the T-slot cutter will have to go in the back as well. It's a bit of an odd thing to do, but I guess that's how it's always done, really. These circular grooves are the only part that couldn't be done in completely manual mode. As I've mentioned, this particular machine is converted to CNC. You could probably do these with a rotary table. It would be an interesting setup. You'd need an angle plate at the very least, or possibly on a lathe. Now, because the groove is at the back and I needed to insert the tool from behind, I forgot to film the squaring off of the casting, but with a horizontal spindle like this machine has, squaring off is fairly straightforward. I also failed to record cutting the groove and cutting the back access hole for the cutter and for the nuts. I wasn't 100% sure that the cheap T-slot cutter that I bought from eBay would work for this job. It's quite a lot of cutting and it's quite a big slot, but in the end it all went quite well. In fact, I did 2 of these with no problem at all, and I could probably do several more. It helps that this particular grade of cast iron is really quite free machining. You can probably see that there's a void in this particular one, so I'm glad I made 2. The foundry did offer to recast them, but to be honest, for what I want, I'm not selling these. This is going to be perfectly adequate and invisible when it's all assembled anyway. I don't anticipate particularly large cutting forces on the cheap eBay high-speed spindle, so all in all I think this will be perfectly okay. Considering this was an inexpensive high-speed steel tool from eBay, I think that all went quite well, really. Because the two parts clamp together with 3 nuts inside the recessors in one of the castings, I needed a back spot face to make a suitable seat for the nuts. This is because the loose parts had to have a draft angle to get them out of the sound. Unfortunately, my camera can't focus very well on things that close, so this is out of focus and we'll just skip through it rapidly. After machining and heat treatment, the cutter was sharpened with a CBN cup wheel that I have in the vertical spindle, and the final result looks like this. Having made the reverse spot face, I could then drill the holes and use it to prepare the clamping surfaces for the nuts. Use the reverse counterbore. The arbor is lowered down through the hole, and then the cutter is screwed on from underneath. This is a rather precarious position in some ways. If the machine or the operator were to demand a rapid retract of the Z-axis at this point, it would get messy quite quickly. There is a small tightening hole in the cutter, but I have forgotten to bring any tool with me to the machine. Conventional screw thread and right hand rotation means that the cutter tightens itself onto the arbor. At this point you have a rare opportunity to see a problem with self-tightening chucks. As you can see, at this point it grabbed tight, tightened itself so hard that it burst the hood of the chuck. It took me quite a while to get this all sorted out again. The dovetail is clamped with 2 bolts that go across sideways. These need a bow to receive them, and these are best cut before the dovetail itself. So I drilled 2 pilot holes, and then switched to the larger drill to drill all the way through. this was about the time that I found that I hadn't put the work far enough back on the table, and in fact my big drill wouldn't reach all the way through.
Bother.
So I was left with no choice but to loosen the part on the table and shuffle it nearer to the drill. This unfortunate oversight does give me an opportunity to demonstrate a way I've found of using a coaxial dial indicator to pick up the edge of an object. I use a square collet block, ER32 collet block like this. These have the handy property of having a perfectly circular hole in the middle, exactly in the middle, and the blocks themselves are a nice round number. I think this is 40mm square. So if I use my coaxial indicator to pick up on the central ball of the collet block, when it's running true I know that my spindle axis of rotation is exactly 20mm from the edge of the casting. So I can use that to work out where I need to be to drill my holes. In theory, because the hole for the collet is tapered, you can also use this to pick up out of square. In fact, I've considered making one with a steeper taper specifically for that job. With the holes made for the clamping bolts, I could then proceed to mill out the dovetail in the top of the bracket. The nice thing about cast iron is you can take off quite a lot at a time. It is generally agreed that a dovetail isn't a dovetail unless it's dovetail shaped. So here we'll find out whether an inexpensive high-speed steel dovetail cutter from eBay can do the job on this big casting. This is actually a 55-degree dovetail cutter, which seems to be the angle of the dovetail on the top of the machine. What I'm doing here is touching off the bottom of the dovetail cutter to the currently machined bottom of the groove. The idea is to make the gap too small, then increase the gap until a dowel of known width will fit through. This is one of my extensive stock of broken 6mm milling cutters. So having passed that through, I now know that I'm 6mm from the bottom and can set on the MDI console above, where you can't see, that distance to 6mm, or probably the thickness -6. At this point I'm measuring the width of the dovetail to get an initial feel for how much more I need to take out. It's a bit of a fiddle with dowels and calipers, and access isn't great, and of course my floor at this point is encumbered with stuff, but this is the way you measure dovetails. There's much better examples of people doing this elsewhere on YouTube. To clamp the dovetail, I need some dovetail clamps, and this is a just fast run through of making the clamps for the dovetails. Starting with a 20mm insert cutter and then finishing out with a dovetail cutter. The special curved T-nuts were made by G-Code and CNC. I think you could do this on the faceplate of a lathe if you didn't have CNC, or making a high-speed spindle like this for your own Harrison milling machine. You will notice how beautifully the camera has focused on the background and not on the work. I made 2 sets of these castings and spindle mountings because I wanted to use the high-speed spindle to engrave a high-speed spindle, and I thought I could probably find a taker for the spare. Rather than use cam, the engraving is done by a subroutine I wrote some time ago. Here we see the subroutine for the digit 0. The G-code works out which digit is required in each position and then carves the major and minor ticks as required. The horizontal spindle here is one I made myself using a harmonic drive actuator. I'll put a link to the blog post on making that in the description.